We're going to look at the next bit of forces and motion. This is connected particles, and then we'll do pulleys after that as well. So we've got a few questions to get through. We'll just do connected particles in this video, and then we'll look at pulleys in the next one. So use the notes alongside for the questions. I'll kind of read them out as well. And again, we're going to be drawing diagrams for these. And these are a bit more involved, a bit more going on. We've got to make sure we take everything into account. So question 1. Two particles P and Q of masses 5 kilograms and 3 kilograms respectively are connected by a light inextensible string. P is pulled along by a horizontal force of magnitude 40 newtons along a rough horizontal plane. So let's get our rough horizontal plane drawn. We've got two particles P and Q. So let's put P here. Let's put Q here. And they've got masses 5 kilograms and 3 kilograms respectively. You might want to put the mass inside, give yourself plenty of room. So P is 5 kilograms and Q is 3 kilograms. So that means they're going to have respective forces of 5G and 3G acting vertically down. And they're connected by a light inextensible string. So between these two things, there is a string. Again, some little things to take into account here. The plane's horizontal that they're on. This thing's horizontal and it's rough. If it's rough, that means there'll be friction acting against the direction of motion of these particles. Also, if they're connected by a string, then there'll be tension in the string. So tension will be pulling this way and pulling this way. If our 40 Newton force, let's say, 40 Newton force is pulling P along this way and they're connected, each of these will also have a force acting upwards. They're going to have a resistance force of, maybe we'll call it R1 and R2, because for every force there's an equal and opposite force. So this 5G acting down, there's an R acting up as well. And we've got particle P experience a frictional force of 10 newtons, so there's a 10 newton force acting along here, friction. So back this way, because the whole system's moving this way because it's being pulled by the 40 newton force. And then Q has got a frictional force acting this way of 6 newtons. Okay, the whole system is moving this way, so this will be a positive direction. And it's accelerating, so let's find the acceleration of the particles. So we're accelerating in this direction, but we don't know what that acceleration is. So at least we've got all our particles set up and we've got the forces acting in different directions. Make sure we always include the tension in the string. Okay, that's really important. That's how it's going to look. So find the acceleration of the particles. So part A. So the whole system is moving to the right, so we can treat the system as a whole thing. We can look at individual particles, but we're going to treat the system as one thing because it's all moving in the same line. Okay, if things are moving in different directions, we can't treat it as one thing. We have to treat them separately, individually, but here we can treat this as one thing. So if we look at our resultant force to the right, we've got 40 newtons acting to the right here. Here's 40 newtons acting to the right. So that'll be a positive 40. There aren't any other forces acting to the right, okay, because we're treating this as a whole. The tensions will cancel each other out because one's going right and one's going left, so we don't need to consider them. So 40 is acting to the right, and to the left we've got a 10 Newton force and 6 Newton force acting against the direction, so minus 10, minus 6, because they're acting in the opposite direction. And that's equal to the resultant force, which is mass times acceleration. Now the mass of the whole system is 3 and 5, so there's 8 kilograms in the whole system. Because we're considering as a whole, it'll be 8 times the acceleration of the system, and then we can solve this. So 40 minus 10 minus 6 is 24. So the system is accelerating at 3 meters per second squared. And I can fill lane at the top. So we're treating it as a whole thing, it's all moving in one line. We've got all the forces acting towards the right, that's the 40. We don't need to include these because they cancel. And then acting to the left is the 10 and the 6. And the overall weight, the overall mass of the whole system, is 8. 5 and the 3 makes 8 kilograms. That's where this comes from. That's part A. Part B says find the tension in the string. So to find the tension in the string, we can't consider the whole system because the tensions kind of cancel each other out. So let's just focus on one part of the system. Let's focus, say, on this part. So for this part, we're going to look at, again, the resultant forces towards the right. So we've got 40 acting towards the right, and that's acting, that's here, that's the only one acting to the right. To the left, we've got T and 10 newtons. And this time we will include T because we're not considering the other T. So minus T minus 10, and that's equal to the mass and times acceleration of this particular part of the system. So here's my mass, 5 kilograms. That's the mass. And we know now that it's accelerating at 3 meters per second. Both parts are accelerating at the same speed, at the same rate. So we're going to get mass, which is the 5 kilograms times acceleration, which is 3. And then we'll get 30 minus T on this side is 15. If we rearrange and solve this, we'll get the tension in the string as 15 newtons. So this is looking at particle P. We could if we want. We don't need to do both now because we've got it, but I'll do it just for the sake of it. So if we focus on particle Q instead, then we should get the same answer. So here's particle Q. With particle Q, if we resolve our forces to the right, then we've got the T acting to the right, the string, minus the 6 acting in the opposite direction, and that's the mass times acceleration. The mass of Q is 3, and we know the whole system is accelerating at 3. And if we look at that, then we get T at exactly the same thing. Okay, so we get the same answer. So we can look at either, whichever one you want, either will work. And then the last little bit, C, a couple of little questions about the inextensible and light string. So inextensible, some little phrases we can learn. The inextensible means that the acceleration of the masses is the same. You just need to learn these little phrases. And the fact that it's light, this means the tension is the same throughout the length of the string. And the mass of the string is negligible, i.e. we ignore it. And they're the two little bits we need to learn for that. So this is connected particles, two things together. We can treat it, because it's moving in one direction, we can treat it as one big system where we include all the mass, all the forces acting, or we can consider individual parts of the system as well. Let's have a look at question 2. So 2 says a light scale pan is attached to a vertical light inextensible string. The scale pan carries two masses A and B. A is 400 grams and B is 600 grams. A rests on top of B, as shown in the diagram, and the scale pan is raised vertically using the string with acceleration 0.5 meters per second. So let's get this drawn. So we've got some sort of scale pan. Let's just use a triangle. It's attached to a vertical light inextensible string, so there's a string here. It carries two masses A and B. A sits on B. So we've got B underneath A. And A is 400 grams. Or 0.4 kilograms. And B is 600 grams, which is 0.6 kilograms. Remember, always working in kilograms, meters, seconds, all those units. The scale pan is raised vertically, so it's going this way. So we'll treat this as our positive direction. And it's got acceleration 0.5 meters per second squared. So it's going upwards, so the acceleration is 0.5 meters per second squared. And remember, we're going to have gravity acting downwards here, aren't we? So we need to take that into account. It's working against gravity. So we're going to have tension in the string, pulling it upwards. So it's going to look something like this. And we're going to have the whole weight of the system is 1g because it's 0.4 g plus 0.6 g. So the whole system is both masses, they're acting down, and the overall resultant force is upwards. So find the tension in the string. So if we resolve our force going upwards, if we look at our system, we've got the only force acting upwards is T. So we'll have T, and then the force acting downwards is both of these together, 0.4 plus 0.6 is 1g, so minus, and I'll just put the 1 in just to indicate that's this plus this. And the overall mass is 1, so this is our mass times acceleration resultant force, and the acceleration is 0.5. So we get T minus G is 0.5, add G to both sides, G is 9.8, so 9.8 plus this, so T will be 10.3 newtons. Again, that's treating the system as a whole for part A. Part B and part C are slightly different. We're going to find the force exerted on mass B by mass A. So let's have a little look. Let's consider A. So if we have, let's give myself a bit more room. If we look at A and what's going on with A here, A, which is 0.4 kilograms, we know that A is moving this way with acceleration 0.5 because the whole system is, so A must be going in that direction. And we know that A is going to have a resultant force acting up against it from B, and it's going to have its own weight acting downwards, which is 0.4 kilograms, 0.4 g. Obviously we've already got the acceleration. So if we're looking at A only, we've got the resultant force is going upwards, and we've got the force of B acting upwards against it, which is R. We've got the 0.4 g acting downwards, so that's minus, and the whole thing is mass. The resultant force is mass times by its acceleration. So this will give me 0.4 times 0.5 is 0.2, add 0.4 g to both sides, and we'll get 4.12 newtons. 0.2. G is 9.8, remember, 4.12 newtons, and that's the force that is exerted on B by mass A. Remember, if B is exerting that force on A, here's A, here's B. If B is exerting that force on A, then A must be exerting exactly the same force back down on B. And then part C. So C says find the force exerted on the mass B by the scale pan. So there's a couple of ways of looking at this. If we look at our overall scale pan, and obviously B is sitting on it, we can actually work out the force exerted on the scale pan by B. Might be easier. So we've got the tension in the string going up on the scale pan. We've got the force being exerted by B on the scale pan. So just looking at the B and the scale pan here, not A, we're looking at a separate part. We know the system's accelerating upwards at 0.5 meters per second squared. So our system kind of looks like this. And for the scale pan, we know the scale pan is moving upwards, so the resultant force is upwards. So we've got the tension in the string going upwards. We've got the force going downwards, and we know that the mass of the scale pan is light, so the mass times the acceleration of mass is 0, so it's 0 times 0.5, so we actually end up with T minus S equals 0, so T equals S, and we know from the first part that T is 10.3 newtons, so therefore S is also 10.3 newtons, and so that's our force exerted on B by the scale pan, same as the force exerted by the scale pan on B.